Hello and welcome to my demonstration of Revolute and Prismatic joints in MOMDYN. So what I'm going to show today is the creation of a simple pendulum and a pendulum with spring physics using Revolute and Prismatic joints. So first we'll create our model. I'm going to call it the joint because it's the joint. Give it the description, demo of Revolute and Prismatic joints. Since it is a pendulum, we're going to want to model gravity. So we'll give it uniform gravity with a gravitational constant of 9.8. So SI units on Earth. Gravity direction minus y. Time duration 10 seconds. And the remaining settings, we'll just leave them at their defaults. Actually, what we will do is we'll set our simulation tolerance a little bit smaller, or quite a bit smaller, 1e minus 6. This is a fairly simple model, so we'll give it a pretty small tolerance, and it should run quickly anyway. So first we see our default empty frame, inertial frame, and origin points. Empty model, I should say. And we're going to start this model by generating our one single constant parameter for mass. Give it the name m, value 1, equivalent to 1 kilogram. And a description. Check that. That's the only instance here where we'll be using the classic interface, and from now on we will be using the joints. So we will start first with a Revolute joint. So the Revolute is very common in multi-body dynamics modeling. It's simply a single rotation angle about a single spatial axis. So we're going to have this be set up to be our degree of freedom in the pendulum model. So if we check the is form box, we'll change it to degree of freedom, set the axis z to 1, meaning z-axis out of page will be the axis about which we define our rotation. The value is the initial value for the generalized coordinate that we'll be creating. We'll say 1 for 1 radian, or about 60 degrees. Give it an initial rate of 2 radians per second. So it will be initially rotating counterclockwise about the page. The last 3 options are spring parameters, or rotational spring parameters. For the moment, we will leave those set to 0. In other words, there will be no spring force acting on this degree of freedom. So if we hit the check mark, we can see in our model, we created the coordinate frame E with axes E sub ax and E sub ay. So that is our rotated frame where the angle defining the total angle between the inertial reference frame and the rotated E frame is that 1 radian that we defined earlier in the Prismatic joint, Revolute joint menu. Moving forward, we'll be defining our Prismatic joint. This joint combines a vector and a point. So if we hit the plus button here, so a couple notable things. One is we want this Prismatic to be attached to the rotated reference frame. So in the reference key menu, we will select A. That means that the vectors that we define next will be defined in the rotating reference frame. For the moment, we're going to keep the is form menu option to constant. So we'll start by defining a simple pendulum that will be fixed length. And instead, what we will do is we will take this x, give it a value of 2, and then the distance defined for the Prismatic joint will be aligned with the E sub ax vector with a total distance of 2. We can think of that as 2 meters. So if we hit the checkbox, we see the vector r sub b and the newly defined point B all aligned with the E sub ax axis. To complete our definition of the simple pendulum, we will go into the bodies menu and click on the particle, give it a name, call it Bob for the pendulum Bob. At the ref point, for the ref point key, we will specify that it will be defined at the point B, and we will give it the mass m, that mass being the first symbolic parameter that we created at the beginning of this video. Hit the check, and we can now see the point mass icon created in the upper right with the name Bob. We can now simulate And you can see this starts to spin about the origin. We initially gave a rate 2 radians per second, and that's enough of an initial rate that it just creates this continuous spinning motion about the origin axis. You can kind of gather that the effect of gravity is there, but not enough to stop its motion before it gets above the vertical axis. The next thing that we will do then, to make this a little bit more interesting, is we will edit our Revolute joint and add a little bit of damping. Specify our Revolute joint A, and below go find this variable C, which is our damping, and we're going to give it a value of 0.5, corresponding to 0.5 Newton meters seconds per radian. And that will be enough that the pendulum will start its rotation, cross the vertical axis, but it won't quite come back up to complete a second rotation. And as we watch it oscillate back and forth, it will gradually over time start decaying down to 0. So we've added or effectively rendered this as a mass spring damper system, albeit with some kinematic nonlinearities related to the restoring force being from gravity, which is dependent on I believe it is the cosine of angle in this case. There's our equations of motion there. So that's interesting enough, but the next thing that I want to do is add some translational spring physics to the prismatic joint. So we'll go into our joints menu again, hit the edit button for the prismatic joint and select B. Now to add the spring physics, what we need to do is take this from its previous case of being a constant and make it a degree of freedom. Now, where previously we just took the x coefficient in the input, we now want to take that value of 2 and put it in the value box, meaning the value of the generalized coordinate at initialization. We can also give it a rate just for fun. We'll say a value of 3. And then down at the bottom, we can add the spring physics. So for K, or stiffness, we're going to give it a value of 50, recalling that the mass value is 1 or 1 kilogram. Think of the natural frequency of the translational system as being square root of K over M. Square root of 50 is going to be about 7 radians per second, or about 1 hertz will be the frequency of oscillation in the translational axis. We'll give it a little bit of damping as well, value of 0.3, and set our equilibrium value to be the same value as the initial condition, or 2. Think of that as 2 meters. Check that I've set this all up properly, and then hit the check button. And there we can see we now have the spring graphic defined, mating up with the R sub B axis, with labels K sub B and C sub B corresponding to the translational stiffness and damping. If we simulate now, we'll get kind of a similar pendulum behavior, but you'll see we now get quite a bit of oscillation in the translational axis corresponding to extension of the spring. We're going to look at our equation of motion now, our mass matrix. So our rotational term, the mass matrix, is M for mass times the QB, or the generalized coordinate squared, angle squared you might call that. And then in the translational axis, just the mass as you would expect, F equals MA. And then forcing characteristics down at the bottom, we can see damping in both the rotational and translational axis, the effects of gravity, and a Coriolis term, that minus 2 MQB SASB. That's our Coriolis force. On the bottom, we have a K sub B. E sub B is the equilibrium length. Q sub B is the distance term in the generalized coordinate. And then the 1M QB SA squared, that's like our centripetal force. We can look at our plot. So first of all, we see the big, large oscillations in the blue term. That's the our angular degree of freedom. So we see about a period of 5 seconds there. And as I noted before, if you look at the period of the the translational oscillation, should be about 1 second per cycle. So very good. As you can see, the joint interface to a certain extent expedites the process of deriving a model with rotational and translational physics, and basically is a step in the path of making MOMDYN somewhat more closely aligned with the current state of the art in multibody dynamics modeling. So that's the conclusion of the video. Hope you enjoyed it. Hope you enjoy using the application. And let me know if you have any questions or suggestions for the app moving forward. Have a great weekend. Take care.